Hi guys, so in this video lecture we'll be taking up Mesomeric effect, but before that let me give some brief on what is the meaning of equivalent RS we just discussed. In our priority order for ARI to compare stability of two compounds, that is aromaticity equivalent RS, resonating structures, hyperconjugation, and finally inductive effect. Right? So I just went through a more precise way of representing what is the meaning of equivalent RS. So the meaning is simple, that a pi electron is moving between atoms of same electronegativity with having equal contribution in the resonance hybrid. Okay, so and all those four rules of resonating structures, that first it's um, what was the first rule? More covalent bond formation. I hope you remember from the resonance video lectures. Complete octet on electronegative element. Third is less or neutral preferred over charged compound. Negative charge on most electronegative element atom. Okay, so those four rules still applies, but you can actually extend that from the E part to the R part. So I think in the previous lecture I compared all these 4 points under the E section, but now after doing some more research and delving into problems further, I figured out the way that equivalent RS you should be seeing the equal contribution, or whether the pi electron or the negative charge or the pi electrons are moving between the atoms of same electronegativity or not. If they are, then the case is finished, it is having equivalent RS. But if it's not the case, then you need to look into the four rules of resonating structures, and this also doesn't happen, obviously hyperconjugation and then followed by inductive effect. Right, so let me just give you a quick example on the same. If we have something like this, then does it have equivalent RS? No. Why? Because the pi electron is moving away from the most electronegative element and going to the carbon atom. Okay, so in this case, do we have equivalent RS? Yes. Why? Because the pi electron is moving from electronegative element and again going back to the electronegative element. Hence it is the pi electron is moving between the atoms of same electronegativity. And does it have equal contribution in the resonative structures? Why not? Delta half. I hope you understand the delta, so I'm not writing into the intricacy, but I hope you have understood the meaning of equivalent RS very well by now. Okay, so let's move on to the mesomeric effect. Mesomeric effect. So it can be broadly classified into two categories. One is plus M. It can also be written as plus R. Another is minus M. It can also be written as minus R. So it is nothing but a different name of the same resonance effect. So plus M means electron donating by mesomeric effect, and plus R is electron donating by resonating resonance effect, or just by resonance. Similarly, minus M means electron withdrawing by mesomeric effect, and minus R means electron withdrawing by resonance effect, or just by resonance. Okay, so let us look into some of the examples to get more clarity. If we have something like this, then N group, the lone pair, it is giving back into the phenyl ring, hence it is donating the pi electrons, hence it is a plus M. And on the other hand, as N atom is more electronegative than the phenyl ring, it is minus I. Okay, second example is, if we have something like triple bonds here, okay, and OH group attached. So this we actually covered into the last few lectures as well as a GK question, or as a GK thing. So this is plus M and again minus I. If we have something like this, then what will happen is, we have in this case actually the nitrogen would be giving to the phenyl ring as well as to this bond. So hence in this case it is plus M, but as nitrogen is more electronegative, it is minus I also. Okay, so let us now look at hyperconjugation. And just for the classification sake only, as we have already discussed hyperconjugation in depth. So we have again can be classified into two categories, plus H, minus H. Okay, so this is simply electron donating by hyperconjugation, electron donation by hyperconjugation, and this is electron withdrawing by hyperconjugation. Okay, so now let's look at some of the examples of hyperconjugation. We have something like this. CH2. Okay, so in this case this CH3 is acting as plus H and plus I for the alkene group. Okay, let us take a look at this example. For this case also CH3 is acting as plus H and plus I. Okay, let us take a look into this example, we have 3 chloro groups attached to one carbon atom and a alkene group. So what will happen is the chlorine group will detach itself, resulting into a positive charge on the carbon atom, which will have some structure like this. So the pi bond is in conjugation with a positive charge, resulting in a resonating structure. Hence it is minus H and minus I. Why it is minus H? Because chlorine group detached itself from the carbon for helping or forming a carbocation or a positive charge here. Hence it is a minus H and minus I. Why is it minus I? Because already 2 chloro groups are attached on carbon atom with the positive charge on it. Obviously it is more electronegative than the alkene group. Okay, so this is the case of minus H and minus I. Okay, so we just a note here that some of the guys may be confused that this is a new thing called minus H for us. Generally we don't do something like that. We remove the chlorine and have positive charge on carbon. So just a note for these guys that yes guys, I'm with you. So just note that don't use minus H usually. So instead compare by inductive effect in place of minus H, right? So just to note it, for the example's sake, I explained you what is minus H, but don't use minus H usually. Just compare by inductive effect in place of minus H. Okay, and minus H is also called as minus H is also known as reverse hyperconjugation. So this is just for your information and knowledge sake in case you are asked in some examination. Okay, so let's look at the summary of what we have discussed so far. Summary is we have plus M. If we have plus M plus H or plus I attached to a carbocation, then it is increasing its stability okay, and if we have minus M minus H minus I attached to a carbon ion, then it also increases stability. Okay, so just a last example before we end off this lecture. I like to give as much examples as possible to my students. Okay, we have this carbocation. This is also called troponium ion, just for information's sake. This is also called troponium ion. Okay. Troponium ion, and we need to compare its stability with phenyl, C plus, phenyl and phenyl. So obviously in this case phenyl will be acting as a plus M group. All the 3 phenyls will be acting as a plus M group for the carbocation, and in this case it is already aromatic compound, and in this case the resulting compound would not be aromatic. Why? Because uh, the overall compound is not aromatic compound because it is not, the overall is not cyclic. If you look into the uh, rules of aromaticity, we have HPCD. So delocalization is there. Huckel rule is followed because 6 into 3 are 18 discipliner, but it is not, overall compound is not cyclic, right? So this is not aromatic, this can be non-aromatic, hence stability is this one. Okay, so in the next lecture we'll be seeing some of the more examples of plus M plus H plus I or minus M minus H minus I effects.